In the last video, we started to talk about the kernels idea and how it can be used to define new features for a support vector machine. In this video, I'd like to fill in some of the missing details and also say a few words about how to use these ideas in practice, such as how they pertain to, for example, the bias variance trade-off in support vector machines. In the last video, I talked about the process of picking a few landmarks, L1, L2, L3, and that allowed us to define the similarity function, also called a kernel, or in this example, if you have this particular similarity function, this is a Gaussian kernel, and that allowed us to build this form of a hypothesis function. But where do we get these landmarks from? Where do we get L1, L2, L3 from? And it seems also that for complex learning problems, maybe we want a lot more landmarks than just 3 of them that we might choose by hand. So in practice, this is how the landmarks are chosen, which is that given a machine learning problem, we have some data set of some positive and negative examples. So here's the idea, which is that we're going to take the examples, and for every training example that we have, we're just going to call it we're just going to put landmarks as exactly the same locations as the training examples. So if I have one training example, if that's x1, well then I'm going to choose my first landmark to be at exactly the same location as my first training example. And if I have a different training example, x2, well, I'm going to set the second landmark to be the location of my second training example. On the figure on the right, I use red and blue dots just for illustration. The color of this figure, the color of the dots on the figure on the right is not significant. But what I'm going to end up with using this method is I'm going to end up with m landmarks. So I have L1, L2, down to Lm if I have m training examples, with one landmark per location of my each of my training examples. And this is nice because it's saying that my features are basically going to measure how close an example is to one of the things I saw in my training set. So just to write this out a little more concretely, given m training examples, I'm going to choose the location of my landmarks to be exactly the locations of my m training examples. When you're given an example X, and this example X can be something in the training set, it can be something in the cross-validation set, or it can be something in the test set. Given an example X, I'm going to compute, these features as so, F1, F2, and so on, where L1 is actually equal to X1, and so on. And these then give me a feature vector, so let me write F as a feature vector. So I'm going to take these F1, F2, and so on, and just group them into a feature vector that goes down to Fm. And just by convention, if we want, we can add an extra feature F0, which is always equal to 1. So this plays a role similar to what we had previously for x0, which was our intercept term. So for example, if we have a training example xi comma yi, the features we would compute for this training example would be as follows. Given xi, we would then map it to f1i, which is the similarity. I'm going to abbreviate it as SIM instead of writing out the whole word similarity, right? And f2i equals the similarity between xi and L2, and so on down to fmi equals the similarity between xi and Lm. And somewhere in the middle, somewhere in this list, at the I component, I will actually have one feature component, which is f subscript I, which is going to be the similarity between x and Li, where Li is equal to xi. And so, Fii is just going to be the similarity between x and itself. And if you're using the Gaussian kernel, this is actually e to the minus 0 over 2 sigma squared. And so this will be equal to 1. And that's okay. So one of my features for this training example is going to be equal to 1. And then similar to what I had above, I can take all of these m features and group them into a feature vector. So instead of representing my example using xi, which is this Rn or Rn plus 1 dimensional vector, depending on whether you count the intercept term, it's either Rn or Rn plus 1, we can now instead represent my training example using this feature vector f, I'm going to write as f superscript I, which is going to be taking all of these things and stacking them into a vector. So f1 I down to fm I. And if you want, and well, usually we'll also add this f0 I, where f0 I is equal to 1. And so this vector here gives me my new feature vector with which to represent my training example. So given these kernels and similarity functions, here's how we use a support vector machine. If you already have a learned set of parameters theta, then if you're given a value of x and you want to make a prediction, what we do is we compute the features f, which is now a rm plus 1 dimensional feature vector. And we have m here because we have m training examples and thus m landmarks. And what we do is we predict 1 if theta transpose f is greater than or equal to 0, right? So theta transpose f, of course, that's just equal to theta 0 f0 plus theta 1 f1 plus dot 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 plus theta m fm. And so my parameter vector theta is also now going to be an m plus 1 dimensional vector. And we have m here because, right, the number of landmarks is equal to the training set size. So m was the training set size, and now the parameter vector theta is going to be m plus 1 dimensional. So that's how you make a prediction if you already have a setting for the parameters theta. How do you get the parameters theta? Well, you do that using the SVM learning algorithm. And specifically, what you do is you would solve this minimization problem. You minimize the parameters theta of c times this cost function, which we had before. Only now, instead of looking there, instead of making predictions using theta transpose xi, using our original features xi, instead we've taken the features xi and replaced them with the new features. So we're using theta transpose fi to make a prediction on the IVE training example, and we see that, you know, in both places here. And it's by solving this minimization problem that you get the parameters for your support vector machine. And one last detail is because for this optimization problem, we really have n equals m features. That is, here the number of features we have in really the effective number of features we have is the dimension of f, so that n is actually going to be equal to m. So if you want to, you can think of this as a sum. This really is a sum from j equals 1 through m. And one way to think about this is you can think of it as n being equal to m, because if f is new features, then we have, you know, m plus 1 features, with the plus 1 coming from the intercept term. And here we still do sum from j equals 1 through m, because similar to our earlier videos on regularization, we still do not regularize the parameter theta 0, which is why this is a sum from j equals 1 through m instead of j equals 0 through m. So that's the support vector machine learning algorithm. There's one sort of mathematical detail aside that I should mention, which is that in the way a support vector machine is implemented, this last term is actually done a little bit differently. So you don't really need to know about this last detail in order to use support vector machines, and in fact the equation that I've written down here should give you all the intuitions that you need. But in the way a support vector machine is implemented, you know, that term, the sum over j of theta j squared, right? Another way to write this is can be written as theta transpose theta if we ignore the parameter theta 0. So if theta were, you know, theta 1 down to theta m, ignoring theta 0, then this sum over j of theta j squared, that this can also be written theta transpose theta. And what most support vector machine implementations do is actually replace this theta transpose theta with instead theta transpose times some matrix inside that depends on the kernel you use times theta. And so this gives us a slightly different distance metric. Like this is a slightly different measure of instead of minimizing exactly the norm of theta squared, we instead minimize something slightly similar to it. That's like a rescaled version of the parameter vector theta that depends on the kernel. But this is kind of a mathematical detail that allows the support vector machine software to run much more efficiently. And the reason the support vector machine does this is with this modification, it allows it to scale to much bigger training sets. Because, for example, if you have a training set with 10,000 training examples, then the way we define landmarks, we end up with 10,000 landmarks, and so theta becomes 10,000 dimensional. Maybe that'll work, but when n becomes really, really big, then solving for all of these parameters, if n were 50,000 or 100,000, then solving for all of these parameters can become expensive for the support vector machine optimization software. That's solving the minimization problem that I drew here. So kind of as a mathematical detail, which again you really don't need to know about, it actually modifies that last term a little bit to optimize something slightly different than just minimizing the norm squared of theta. But if you want, you could feel free to think of this as kind of a implementational detail that does change the objective a bit, but is done primarily for reasons of computational efficiency. So you usually don't really have to worry about this. And by the way, if you're wondering, in case you're wondering why we don't apply the kernels idea to other algorithms as well, like logistic regression, it turns out that if you want, you can actually apply the kernels idea and define these sorts of features using landmarks and so on for logistic regression, but the computational tricks that apply for support vector machines don't generalize well to other algorithms like logistic regression. And so using kernels with logistic regression is going to be very slow. Whereas because of computational tricks like that embodied in how it modifies this and the details of how the support vector machine software is implemented, support vector machines and kernels tend to go particularly well together. Whereas logistic regression and kernels, you can do it, but it's going to run very slowly, and it won't be able to take advantage of advanced optimization techniques that people have figured out for the particular case of running a support vector machine with a kernel. But all this pertains only to how you actually implement software to minimize the cost function. I'll say more about that in the next video, but you really don't need to know about how to write software to minimize this cost function, because you can find very good off-the-shelf software for doing so. And just as I wouldn't recommend writing code to invert a matrix or to compute the square root, I actually do not recommend writing software to minimize this cost function yourself, but instead to use off-the-shelf software packages that people have developed. And so those software packages already embody these numerical optimization tricks. And so you don't really have to worry about them. But one other thing that is worth knowing about is when you're applying a support vector machine, how do you choose the parameters of the support vector machine? And the last thing I want to do in this video is say a little bit about the bias and variance trade-offs when using a support vector machine. When using an SVM, one of the things you need to choose is the parameter C, which was in our optimization objective. And you recall that C played a role similar to 1 over lambda, where lambda was the regularization parameter we had for logistic regression. So if you have a large value of C, this corresponds to what we had back in logistic regression of a small value of lambda, meaning of not using much regularization. And if you do that, you tend to have a hypothesis with lower bias and higher variance. Whereas if you use a smaller value of C, then this corresponds to when we're using logistic regression with a large value of lambda, and that corresponds to a hypothesis with higher bias and lower variance. And so a hypothesis with large C has a higher variance and is more prone to overfitting, whereas a hypothesis with small c has a higher bias and is thus more prone to underfitting. So this parameter c is one of the parameters we need to choose. The other one is the parameter sigma squared, which appeared in the Gaussian kernel. So if the Gaussian kernel sigma squared is large, then in the similarity function, which was this, e to the minus x minus landmark, right, I squared over 2 sigma squared. In this 1D example, if I have only one feature x1, if I have a landmark there at that location, if sigma squared is large, then the Gaussian kernel will tend to fall off relatively slowly, and so this would be my feature fi, and so this would be a smoother function that varies more smoothly, and so this would give me a hypothesis with higher bias and lower variance. Because the Gaussian kernel that falls off smoothly, you tend to get a hypothesis that varies slowly or very smoothly as you change the input x. Whereas in contrast, if sigma squared was small, then if that's my landmark, and given my one feature x1, my Gaussian kernel, my similarity function, will vary more abruptly. In both cases of peak at 1. And so if sigma squared is small, then my features vary less smoothly. So if, just have higher slopes, higher derivatives here. And using this, you end up fitting hypotheses of lower bias, and you can have higher variance. And if you look at this week's programming exercise, you actually get to play around with some of these ideas yourself and see these effects yourself. So that was the support vector machine with kernels algorithm. And hopefully this discussion of bias and variance will give you some sense of how you can expect this algorithm to behave as well.